Hello, calculus fans. So we talked about one of our models for population growth, and it was based on the assumption that the population grows at a rate that's proportional to the size of the population. So our differential equation was dp by dt is equal to k times p. That k is a proportionality constant. This model can be applied to actual populations of bacteria or other animals, even humans. It can be applied to chemical reactions and even to the growth of money in an interest-bearing account. Now the model actually even works if the population is decreasing, in which case our proportionality constant will be negative. And that's useful in the context of things like radioactive decay, which we'll see later on. Now the equation is separable, so we have a technique for solving it. Now instead of p, we'll use y, and that'll give us a generic equation. So I don't want to think of p as just being a population. It can be lots of different things. So if we separate variables, we'll get dy over y is equal to k dt. We integrate both sides, and we get log of absolute value of y is equal to kt plus c. We can get rid of the log by doing an exponential. And so we end up with e to the c times e to the kt. And instead of e to the c, we'll rewrite that as a. And we can also drop the absolute value because the a that we're going to deal with is either plus or minus e to the c, or it's equal to 0. But it's an arbitrary constant. So that takes care of the absolute value thing. So notice that when t is equal to 0, y is equal to a. So a actually has a meaning in this context. It is the initial value of the population. So just a quick summary of what we've actually computed here. The solution of the differential equation dy by dt is equal to ky with initial condition y of 0 is equal to y naught is equal to y of t is y naught e to the kt. So we're going to use this quite a lot. So anytime we run into this differential equation, we know what the solution looks like, so we don't have to solve it each time. Okay, that's all for now.